So we didn't have a really strong predefined topic for this week. And Lan asked some interesting questions, and Eric asked a couple of interesting questions. So I thought maybe you might address some of those things. They're pretty fundamental issues that people run into when they do image analysis, and it's worth posting the video up there on these topics anyway. It kind of relates to what we were talking about in the last couple of lectures about making artificial data. Well, some of it relates to making artificial data. So I will tell you something that I have seen many times over the couple of decades, coming up on 3, I guess now pretty soon, that I've been in the CryoEM community. Let's say you write a new algorithm and you want to publish that new algorithm in a paper. What are the expectations for what goes into that paper? If you're a mathematician, you might say, well, I'll put together some good realistic simulated data, and I'll test my algorithm on that, and then I'll publish my paper. The response from the reviewers will be, great, but you need to test it on real data too. If you only test it on real data, then you don't have any ground truth data where you can test it against, right? Then you're only testing, you're sort of assuming that the answer is obvious enough that people won't complain about your lack of having sort of knowing what the ground truth is. And what that often leads to is people working in this area spending an inappropriately long time trying to generate very realistic test data. I am aware of at least 2 specific cases where people put together systems for generating very realistic simulated cryo-EM data, and they spent 2 or 3 years on it. And that 2 or 3 years resulted in a publication about the method for generating test data, which would go in something like ultramicroscopy or some impact factor 1 journal or something like that. And then they used it in their one publication, and said, well, now I've created this and a whole bunch of other people use it. Generally speaking, no one else will be able to figure it out, and no one will be able to use it. And they basically wasted 3 years of their life because it doesn't add much to the final paper. In other words, if you use really, really carefully simulated test data versus using very, very roughly simulated test data, which you could do quickly, as long as you sort of demonstrate that your algorithm works with the test data, whichever kind it is, it's fine. And what people really care about is whether it works on the real data, right? So you demonstrate that it works on some sort of test data, even if it's really poorly designed test data, and then you demonstrate that it works on real data. And it doesn't really ever matter that you spent a lot of time generating your test data. Now, to be fair, if you do a really bad job making your test data, the reviewers will complain about that too and say, you didn't even take CTF into account or something like that. And then you'll probably have to do a slightly better job in making your test data to get your paper published. But it's something that, if you're spending more than 2 or 3 days generating your test data, if you're spending weeks or months generating your test data, then you're spending too much time. And I wanted to talk a little bit about what the differences are between actual cryo-EM image data and the sorts of things people often generate artificially. So this gets directly to Lan, who had made some made some synthetic data trying to sort of emulate organelles in a cell. So what she did is she made some 2D ellipses, and then she added a bunch of noise to the 2D ellipses, and I think maybe she applied some CTF to it. And then she tested it against her algorithm. She tested it against Muyuan's old algorithm, and they both work perfectly. It's like, yep, that's what's going to happen. They're both going to work perfectly. And the test that she did, the data was pretty unrealistic, and you would expect pretty much any algorithm to be able to work perfectly. If it doesn't, if an algorithm doesn't work on that data, it's not a good algorithm for sure, right? So let's talk about maybe why that is bad. So let me share my screen, and I'm not showing you LAN's actual data here. I'm gonna just do some more simulation stuff myself. Let's try. Yeah, let's go back to some of the stuff we were doing previously with adding noise and CTF to things, and take a look at that. Let's see. Oh, is the font size too tiny for everyone? Do I need to make it bigger? I didn't reduce my screen resolution this time, so it's...
I guess it's a little small, but it's readable.
All right, let me do this. I'm guessing that's better.
Yeah, that looks good.
Is it still shared?
Yep. Yeah.
It lost its green box. All right, I'm going to stop sharing, and I'm going to start sharing again just to make sure it's not going to mess up the recording. Huh. Still no green box. Well, all right. Well, I'm just going to assume that it's going okay.
Yeah, we can see the screen.
All right. All right. I guess I don't know what I was using for that. Let's see what we have. It's all right. Yeah, projections. I think that's what we want to do. Yeah, so these were the random projections that we made previously. And I'm going to run those through E2 filter tool again. Oops. There we go. Right. So we had our math.simulate CTF processor, and then we had our math.add sig noise processor that we used. And if we turn on the CTF, we can see that. And if we turn on the sig noise, then we can hide it behind a bunch of flat band random noise. All right, now the question is, what's wrong with this? Right? What is unrealistic about this simulation? So we took a PDB file, we made projections of the PDB file, we applied a CTF filter to the PDB file, so we got rid of a lot of the low resolution stuff and that sort of thing. And then we added some noise to it. So what aspects of this would make this unrealistic CryoEM data?
No motion.
That's a good point. No motion. That's one important thing. Any other ideas? What else might be missing? All right. How about the fact that if you're looking at a real CryoEM image, what's noise in that image? What would you consider noise to be? Most people would look at the image and say, well, so there are two ways of looking at it, right? One way is, there's this noise generated by the imaging process itself, right? So there's so-called shot noise, which has to do with the fact that you're broadcasting a finite number of electrons, and when you count the electrons, there's inherent uncertainty in that counting process, and that produces so-called shot noise. Then there's additional noise sources in the detector itself. The detector is going to produce a certain level of background noise. So if you just image a dark detector, you don't get zero everywhere. You get some non-zero number of counts. On counting detectors, it's fairly minor, but it still exists. So all those sources of noise are great, and you'd say they're pretty fundamental, and they're not quite flat band. I mean, the noise that we're adding here is so-called flat band noise. If you look at the Fourier transform of the noise, it's going to be flat. it's going to have a constant Fourier transform intensity. So, all right, let me go ahead and do that. Let's this view. I'm going to add a 2D view again, where we can look at the power spectrum, and I'm going to compute the average power spectrum of the stack. And we're going to look at that again. I know we looked at that last time, but we'll look at it again. Put it on a log scale. And what we see is, so I'm just making sure that I've got, yeah. So what we see here is basically flat noise, right? It's even pretty flat all the way out here. It's just that the sampling of the data isn't fine enough to sort of see it getting down to the flat level, but basically the noise is flat across here. If you look at the actual Fourier transform of a real CryoEM image, it won't look like that. Let me see if I can find an old presentation somewhere we can take a quick look at.
Does that partly have to do with?
We don't need to look at that. What?
I mean, you also have the ice variable. Is that also?
Well, there's more we're going to talk about. Don't worry. But I'm going to start with this. Let's see. So I'm just trying to remember the last time I talked about that topic. Now, or maybe not even the last time, but a time I talked about that topic. Oh, maybe there. Tomography, 3D classify, maybe. Let me just look and see if it's in here. No CTF there. Sorry, it's a standard thing I've gotten a whole bunch of my talks, and I just no, I probably need to move before 2018, huh? Didn't go many places. Oh, let's try this. Okay, particles. There, finally. Okay, CTF and MTF, right? So this is a power spectrum of, all right, we'll start. Here's an actual CryoEM image. You can see it's got a little bit of ice contamination. It's got a bunch of particles floating around in the ice, and then it's got a background. If we compute the Fourier transform, looks like that in 2D. In 1D, it looks like this. Okay, what do we see? Well, we see the CTF oscillations. We see a big peak here at low spatial frequency. And then if you connect the dots through all the zeros of the CTF, you can see it is definitely not flat. So if you look at people that do you know, like Shores when he wrote Reliant or something like that, one of the assumptions that goes into maximum likelihood algorithms is that you have flat band random noise in the background, meaning that the Fourier transform of the noise by itself should be flat in Fourier space. And that, so if you, all right, how do we put this? If you have uncorrelated noise, so if you have noise where the randomness in every pixel is completely independent from the randomness in every other pixel, and you compute the Fourier transform of that sort of noise, it will be flat band. Okay. The assumption that goes into the derivation of maximum likelihood in CryoEM is that the noise that's present in CryoEM images is flat band noise. Now, the shot noise that comes out of the imaging process and the noise that comes out of the detector is close enough to being flat band random noise that that assumption is fairly valid. Although usually it's not quite flat. Usually there's a little bit of a filter that's effectively been applied. So it's pink noise. It's been low pass filtered a little bit by the imaging process. So typically what's done in Reliant and some of the other packages is so-called flattening process, where you fit this curve, and then you adjust it so the noise becomes flat. And you've also amplified everything else. You're filtering everything together at the same time, which is unavoidable. And the assumption is that if you make the noise flat, then that's going to produce the desired uncorrelated noise, background noise that you need to work with. Unfortunately, there are some pretty fundamental flaws with that assumption. First of all, while it is absolutely true that shot noise is uncorrelated, it is not at all true that you can take correlated noise and flatten it and produce uncorrelated noise. Okay, it is a logical flaw, and it is considered to be a weak enough flaw to be not so flawed that it's a good enough approximation that they can get away with it. And it's true to an extent. While the maximum likelihood theory was derived under the assumption that the noise was flat band random noise, it's not clear how strong that whether that's a requirement or whether it was just an assumption. If you got rid of that assumption, maybe maximum likelihood stuff could still be derived as being correct. Anyway, so that is one hole in the sort of the whole maximum likelihood theory as it's used in CryoEM right now, is the fact that the noise is not really uncorrelated, and it's not white, and they whiten it and then they just sort of assume it's okay. But there's more issues than that. If you look at what's in the image, their assumption is that anything other than that flat band random noise in the image is noise, right? So, sorry, everything other than the noise is noise. No, that's not what I meant to say. Sorry. Everything other than the noise, that flat band random noise, is signal, right? Is particle data. Is also obviously not true, because, for example, that's not particle data and that's not particle. And you say, well, I'm only boxing out the particles. But the assumption then is that there's nothing floating around in the ice other than the actual particles that you're trying to image. In other words, when you purified your protein into pure water, with no other buffer molecules or anything like that. And the protein doesn't degrade at all. There's no little bits of protein floating around in solution or anything else. That you basically have pure ice, pure water ice with protein molecules floating around in random orientations. That's obviously nonsense, right? We have obvious aggregates and stuff like that. And there's all sorts of other little lumps that you see floating around. That's not flat band random noise. That's other junk floating around. And when you think about it from the perspective of doing a 3D reconstruction, the noise problem isn't the same. The noise problem, when you think about a reconstruction, is anything that isn't a perfect projection of a perfect particle which matches the final structure is noise from the perspective of the reconstruction algorithm. Okay, so in the case of the math, you're saying that noise is this perfect white stuff, and everything that isn't noise is signal. But from the algorithm that you're using to actually do the reconstruction, your assumption is that noise is only the perfect particles that are projected, perfectly projected. That's the signal, and anything other than that is noise. So there's this big disconnect now between what noise is in the mathematical derivation and what noise is in the actual image data. So from the perspective of doing 3D reconstructions, the noise is anything that isn't the particle. And that stuff has structure because it's real stuff that's floating around in the ice. It's just real stuff that isn't the molecules of interest. So that's another source of noise that's present in the image data. What impact does that have? So back to our simulation again here. So we've got our simulated data here. And what we did is we took a PDB file and we turned that into a pseudo electron density map by putting Gaussians where all the atoms are. Then we performed a CTF filter and we added noise. So not only did we not add all the other random little bits of protein and buffer and stuff like that that are floating around in the background, we also have a really big problem, which I think I did mention when we were doing this, which is that the PDB map, the PDB data that we use to generate the projections is not solvated. It's in vacuo. There are no water or solvent molecules around it in the PDB file. And when you make a projection of that in vacuo thing, that means that you have a strong average density compared to nothing outside the protein. So it's sort of like you have the actual the high resolution structure of the protein is absolutely fine, but then there's this sort of step function as you go from the vacuum up to the protein. And by not solvating it correctly, you cause all sorts of additional problems from the sense that it makes the reconstructions a lot easier than they are in actual cryo-EM data. So even though visibly you can produce something which looks a lot like cryo-EM data, there are some real mathematical outliers, problems with the data from that perspective. Maybe just to sort of think about Land's problem, Land was trying to simulate just like a sphere, a circle, or an ellipsoid or something like that, pretending that it was some sort of a vesicle or something like that, and do that in a way that was sort of a good simulation. But again, what she did was she just took basically black, 0 everywhere, and then she put an ellipse, which was 1 inside the ellipse, and put that down in space. And that's a very, very strong, low resolution object, right? Almost all the information in that object comes from the fact that the mean density inside the circle is different than the mean density outside the circle. Applying the CTF to that object helps make it more realistic, but it does not undo the fact that you simulated this really strong mean contrast difference between the objects. There are other problems as well. For example, I think I can actually pull this up still. No, I actually closed it. Let me go back into it again. I'm going to stop sharing for just a second so I don't show anyone stuff that is proprietary to other people's other groups or something like that. Let me see. Okay. Be back in just a second. Okay. Share. So what we're looking at here, obviously these are downsampled a lot. These are just thumbnails of a sort, are real extruded vesicles floating around in solution. I think these are POPG, maybe? POPG, yeah. So these are POPG vesicles floating around in solution, just imaged in 2D. Now, if you look at these vesicles, you'll note that actually the density inside the vesicle is a little different than the density of the bulk solution outside. So there is some real difference there. And the reason for that is, of course, there's phosphates in the lipid head groups. And the phosphate has a very high electron density. So even though we're applying this pretty strong high-pass filter as part of the contrast transfer function, you still get a little bit of that sort of overall contrast effect left. Now, of course, you notice that there's a really dark ring around the outside edge. And a lot of people, when they look at that, they start thinking like, oh, I'm looking at like a slice through the middle of the vesicle or something like that. And no, of course you aren't. You're looking at a projection. You're looking through the entire vesicle. The reason you see the dark edge around the outside is because you're looking through a tall vesicle. You're looking at the profile of the lipid bilayer here. So you're looking through a large number of phosphates on the edge, and in the middle, you're just looking through 4 layers, right? The inner and outer bilayer on the front and back surface of the vesicle. So the strong density that you see there is due to that fact. Now, I guess I didn't pick the very best project. You can't actually really resolve the bilayer very well here. But in a couple of these images, you can maybe begin to resolve it. I think these images were just taken a little bit too far from focus. So the other thing to be aware of, though, is that while there is a little bit in a in a real lipid vesicle, while there is a little bit of overall contrast difference because of the phosphate versus water background, there's also a lot of variability in the texture of the lipid bilayer the lipid bilayer itself. So the lipid bilayer is two-dimensional. It's a liquid crystal, meaning that one dimension is constrained, in 2 dimensions it's a liquid. But it's a liquid that still has real size to the tails of the hydrocarbon chains have an actual size to them, and that causes an exclusion radius, which means that there are characteristic length scales. We look at the Fourier transform of this, you'll see lumps corresponding to the size of the lipid molecules and to the size of the tails and that sort of thing. There's a lot of structure in this, even if it's randomly structured. So if you look at the power spectrum of a lipid vesicle without any of the background noise or anything like that, it's not going to be flat in Fourier space either. It's going to have all these lumps and features in it because of this texture that's present. So that sort of thing also isn't getting properly simulated. So if you asked me, how would I go about maybe simulating some sort of an ellipsoid or something like that and try and make it look more like realistic cryo-EM data? I kind of want to avoid this issue of having of having my algorithm focus on the mean density inside versus outside. Because if you go closer to focus, that fades very quickly. Very quickly, you'll see that there's almost no difference between the inside and the outside as you get closer and closer to focus, because you're doing more and more of a high pass filter. So you really don't want to have too much of that present. But what you do want to have is this difference in texture. So basically the texture inside the vesicle is going to be very different than the texture outside the vesicle. So I think what I would do is I would do something like take flat band random noise and apply some sort of a filter, a band pass filter, something like that, to produce texture in the noise, then mask it out, and then merge that in with masked out noise with a different background signal. Right? So what I'm producing is a difference in texture rather than a difference in image. So maybe we can try doing something like that. I haven't really tried this before, so we'll just see what we can come up with. So let's try. Often, so there's a function test image. I think we may have talked about it before. Which will make 2D test images of various sorts. Some of these are things like squares or hollow squares or that sort of thing. So we could use something like that. Or another approach would be you can just make a whole image full of noise, and then we can apply a mask to it. So maybe that's a good thing to do. Let's try that. We'll do that with filter tool. So I'm going to make an empty image. And for those of you who aren't aware of it, there's a nice shortcut in E2proc 2D or E2proc 3D, which allows you to make an empty volume. Actually, I want to say :0. So this will make a 256 by 256 image and set all the pixel values to 0. And I'm going to call this x.hdf. Not adding noise or anything like that to it right now. And of course, it gives me a warning. Oh, sorry, yeah, I have to say write junk. Normally, if you run E2proc 2D on an image stack and it finds an image that has 0 standard deviation, in other words, all the pixel values are exactly the same when it writes it to disk, it skips that image because it assumes that it's some sort of a bad image. If you say write junk, then it will still write it out. So let's run filter tool on that. And I'm going to make a new filter. We're going to call it sim noise. And we're going to do math. Add sig noise. Actually, sig noise won't work because I don't have a standard deviation. So just add noise. Noise 1. We'll turn that on. Okay, so now we have flat band random noise in an image. Terrific. Now I want to add some, so I want to make this noise textured. Right now, this is exactly what the what the maximum likelihood mathematicians assumed in their derivation. This is flat band random noise. No pixel value is correlated with any other pixel value. It's basically a Gaussian distribution of values in real space, independent in every pixel. Okay, so now we add texture to it. So the way we add texture is by adding some sort of a filter. So let's try filter dot. We could try a bandpass filter. Why don't we just use a CTF filter? That'll produce something which is kind of textured like the texture that you get from a contrast transfer function. So again, this is just pure noise. So let's math dot. Oh, sorry, that's filter. I think it's math dot simulate CTF. Right. So the same thing we were doing before. Now we're adding noise first, but now we're filtering the noise. So this is exactly what we were doing before. We just sort of switched the order. Well, and I didn't have. There's no sig in this because I'm not using the standard deviation as a basis.
What would the CTF filters? What would the CTF filters have done? Because there was like a CTF underscore and I think a CTF in the filter tab. There were things called CTF, I believe. When you're in filter.
This one, or you mean under filter?
Under filter, yeah.
Okay.
And then so the top one is
CTF underscore. I have no idea what that one actually does. CTF is applied in a Fourier image. Looks like it does something very similar to the one that we're using. It has an underscore in it. I don't know who added it or why.
Okay.
And then so it may be that this one will work just as well as the other one that we were using. But I'm going to use the one that I know works.
Sure.
You unfortunately will run into that when you have any project like this, which is kind of modular, and 25 people have worked on it over the years, that someone doesn't realize something exists, so they add it themselves. There are also issues with Paul Penchek when he was working on Sparks, which is jointly distributed with EMAN2. He didn't trust a lot of the stuff that we had written. He kind of only trusted his own code. So he had a tendency to kind of rewrite things, even if it already did exist in the system from time to time, which is fine. In some cases, we switched to using his version because if he wouldn't trust our code, well, we'll show him and trust his code. But anyway, we'll pick some parameters here. 10% amplitude contrast, B factor 200. We don't need that, or we leave it on, but it's 0. We'll assume that we have a perfect microscope nearly here. Defocus of 3 microns, no noise. We'll leave it. Yeah, we'll just turn that off. We don't need the phase flipping. Voltage 300. All right, so some basic CTF parameters here, and we'll turn that on. Okay, now suddenly our noise has structure, right? So you might look at that and say, wow, that actually looks a lot more like what I often see in the background of a CryoEM image, right? I mean, it seems to have some sort of texture to it, which it didn't have before. Well, it's still pure noise. It's just that we've applied a filter to the noise, so certain frequencies of noise are stronger than other frequencies of noise, right? So if we look at the power spectrum of this, again, we have that 0 peak, which is humongous, but we can zoom in here. So if we look at the power spectrum of this, ignoring the 0 peak, you can see there's the CTF pattern, and it damps off fairly quickly. But yeah, anyway. Oh, the only other thing is I didn't pick an angstrom per pixel value. I probably want to modify that to something more like 3 or something, just to make our power spectrum a little bit better. Yeah, now you can see the power spectrum is a little smoother than it was before. Right. So we can do something like that. And now we could say, all right, what I'm going to do now is I'm going to mask. Oops. Yeah, there we go. We're going to add a mask dot. We're going to do a hard mask. Well, maybe we should do a soft mask. We'll do a slightly soft mask. So we'll mask from the middle of the image. We'll make the outer radius 40. And it's basically going to be 0 outside the mask. And we'll give it just like a 2 pixel edge. So it's just a little bit soft. So it's not a really sharp edge. Okay. Then turn it on. And ta-da, we've got some masked out textured noise. Okay. So we can go ahead and save that. If I switch, I can go ahead and, I guess it doesn't consider it a stack, so it won't let me process. So I'll have to go to the command line and I'll have to do the actual process.
What is the purpose of masking in this case? I mean, I understand what you're doing by masking.
What I'm doing is I'm trying to create a simulated circle, which is a reasonable test object. So what I'm going to do is I'm going to create textured noise for the inside, for the object itself, and then I'm going to create non-textured noise or differently textured noise for the background.
Gotcha.
Okay, so right now I'm using this outer radius 40, inner radius 0. And then my plan is I'm going to change this to 40, and I'm going to change this to whatever, a big number. And I'll make another type of noise for the rest. And then I'll add the two together.
Gotcha.
So I'm just using filter tool as a way of picking the parameters that are useful for this process.
Gotcha.
Okay. So we can quit this now. And we should have filter tool sim noise, which has the processors that I was using. So I can now say e2 proc 2d.py 256 0 test circle.hdf, and then we'll put our 3 processors in a row. Okay, and now we're going to do it again, but this time we're going to make the outer radius, the inner radius 40, and the outer radius a big number. And we're going to, well, let's just get rid of the CTF entirely and see how that looks. Noise 1, seed 0. Yeah, that should be okay, I think. And let's see what we wind up with. Oh, and I need to change the output file name, or I'm going to overwrite it. Test.hold. Okay, so now if we do E2 display, we will see we have test.cir, or sorry, test circle, and we have test hold. Okay. So now in Python, we can A equals em data test sir.hdf. B is em data test whole.hdf. C equals A plus B, C.write image test object.hdf. Okay. Now, I know we could do it from inside JupyterLab, but I'm just going to do it this way this time. So we have test object, and it looks like this. Okay, so you can see we had a little bit of a mismatch. in sort of how strong the noise was. So when I filtered out the when I applied the CTF to the noise, I reduced the total amount of power that was present in the noise image. So if you integrate under the power spectrum of the flat band random noise, you get a big number because it's flat. And then if you integrate under the CTF modified curve, it's massively lower, probably a factor of 2 or something like that. So we need to do one other thing. We're going to go ahead and say a.process in place normalize, and b.process in place normalize. And we'll just overwrite the output file, hopefully. Yeah. Oops. Oh. Ah, there we go. Okay, so even after normalize, you can see it's still not quite perfect, and that's because now it's made the signal in the regions where it's strong really strong. So we didn't add any of this background noise to this object. We made a hole, and we put just this noise here, and we put just flat band noise out here. So this is still probably a little bit stronger than we want it to be.
What if you normalized the added image? Would it flatten?
I normalized both of them.
No, but after you add them instead of before.
After you add, normalizing this would look exactly the same. It's normalized as part of the display process.
The filter, I thought, is still a little bit different than CTF, but yeah, okay.
No, the filter is different. I'm just explaining the sorts of issues that we're going to run into when you try and do this kind of simulation, right? You think you kind of have all your bases covered, and yet you run into these sort of misnomers. Right. So typically what you do in a situation like this is either you're going to add this noise on top of this noise, and that's going to sort of mix in, and that's actually probably fairly realistic, or you may make some sort of heuristic adjustment to this. So let's try the first approach. I'm going to go back to the command line, and I'm going to make the quote the whole image just pure noise. Pure noise. And I'm going to get rid of the mask processor. So we're just going to make a random noise image. And now, pure noise. And I think we can probably get rid of our normalize here too. It doesn't really matter too much. And we'll call this test object 2. And let's see how that looks. Test object 2. Ah, okay. So that's maybe a little bit better, I guess. So now what we have is a textured circle overlaid on top of the flat band random noise. Now, it depends a little bit on what you're trying to simulate in a certain sense, right? If you're thinking about, say, oh, there's a vesicle in solution that's floating around, then you'd say, well, the volume where the vesicle is, or say you've got a protein in solution floating around, where the protein is, it's excluding the solvent, right? So you don't want to have the solvent noise where you have the particle, the structured particle data. But from another perspective, a lot of the noise is just shot noise, which is coming from the actual imaging process. And that shot noise is going to be present in every pixel location, not just the pixel, it's not going to depend where the protein is or isn't. So there's a certain component of the noise which is dependent on coming from the solvent itself. And then there's another component of the noise which is coming from the shot noise and other noise sources, detector noise and that sort of thing. So this is where you start going down the rabbit hole and saying, oh, if I really want to simulate this right, now I really have to sort of simulate the entire process of the microscope. I've got my really simple CTF simulation. I should use a better CTF simulation. I should simulate the whole imaging process of the microscope or something like that. And you can make this process infinitely complicated. I would say for purposes of detecting an object in space, that's probably good enough. And if you say, oh, that object is too weak to detect, the extra contrast that we've added isn't enough, well, make it a little bit stronger, something like that. The goal is to produce something which, if you look at the power spectrum of this, and get rid of that 0 peak, what we should see is sort of flat noise with some little lumps for the CTF where it is. And you can see this is really weak. We're barely seeing the CTF at all. So we'd probably be justified in amplifying our textured noise signal quite a bit more than what we're doing here. So let's take one last step and we'll do that. I'm going to take my circle noise and I'm going to a.mult. I could say a times equals, but then that's going to make a copy. I'm just going to multiply it in place, and let's make it say 5 times stronger just so we see a nice effect. Okay, and now if we look at the image, oops, no, that's fine. That didn't do any harm. Okay, now it stands out pretty clearly. And now if we do a power spectrum and we zoom in past all of the CTF stuff, sorry, all of the. Okay, now you can see noise is up here, right? It's not the zeros aren't going down to 0, right? The noise level is up here, but now you can see the CTF sitting clearly on top. So probably we want something in between those two extremes, right? So you might play with that with filter tool or something if you want that. That would be one approach. Or anyway, since we're not putting a hole in the noise anymore in this approach, we could actually use filter tool to sort of manually adjust this, right? Because we could read the circle that we cut out in as the raw image, and then we could just add noise to that image until we were happy with the level. All right, so I think that's probably most of what I wanted to say about noise simulation. There was one other question which I thought I might address today. Does anyone have any questions about that simulation stuff? No?
It's a little bit more complex, but it would be getting into like how would you make a more complex shape then, if there would like if you wanted to make like an I don't know, just like an S-shaped object or something like that.
Well, it depends on if you want the object to be really like an artificial object where you have sort of a proper ground truth for it, that sort of thing. I would probably just go into a paint program and draw a picture, and then use that as a mask.
Gotcha. Okay.
Right. So I used a circle as a mask here, but you could use any other image as a mask if you want. It should just be 1 and 0.
Right.
In fact, you could actually draw it and then you could maybe low pass filter it slightly so it had a slightly soft edge. That might be a worthwhile thing to do or something too. Anyway. Okay. So the other question that came up was about HDF and storing things as HDF and some of the confusions that you run into if you start doing deep learning stuff in TensorFlow with HDF files. So EMAN has this HDF file format that it uses. This is HDF5. It's a standard file format, interdisciplinary standard file format. It has its own organization that professionally maintains it. And it is considered the standard in a number of different scientific communities. So the climatology community and astronomy community and I think some of the high energy physics communities. There are a number of different communities that have sort of adopted HDF5 as their standard data file format. So there was a proposed. So the thing about the HDF5 file format is that it's complicated. It allows you to store sort of arbitrary data, n-dimensional data with arbitrary precision and arbitrary metadata. So you can put header information, arbitrary header information into these files as well. It supports lots of different types of metadata. So it's a fairly complicated file format from the perspective of having a lot of capabilities. But it does deal with all sorts of issues that people have otherwise had to deal with in the past, with big Endian machines versus little Endian machines, and different floating point representations. And so there's a whole swath of problems that historically data scientists had issues with, which the HDF file format solves for you. The complexity with HDF is that it's kind of like a file system. The file, if you have an HDF5 file, the contents of that file are organized kind of like a file system. So if I use a standard HDF5 utility and one of these image files that we've created, so there's a program called H5 dump. Very often the extension that you use with HDF is H5 instead of HDF, but either is okay. Anyway, so there's a program H5 dump which will let you look at the raw contents of an HDF5 file. So let's say H5 dump test obj.hdf. Oops. And we'll pipe that through less. Okay, so what that'll do is it'll show you this sort of hierarchical structure. Looks almost like dictionaries or something, right? So here's the file. Inside the file, there's a group slash. Inside the group slash is a group MDF. Inside the group MDF is a group images. And images has the whole images group has an attribute, the maximum image ID, that says how many images are in the file. So this says that the highest numbered image in the file is image number 0. And then there's a group 0. So this is the group which contains the first image. Then there are attributes, and these are all the header values which are present in the EMAN object. You can see EMAN is complex real imaginary. So these are all the header values that you get. If we go here and we say a dot get attribute dict, we can see the entire header, and the values that we see here would exactly correspond to the values that you see here, although in the HDF5 file, EMAN prepends the EMAN specific header items with EMAN, so they can be distinguished from non-EMAN associated ones. And then finally, after we get through the header, we get down to the actual data set itself, which has these dimensions, and it's stored as a 32-bit floating point numbers, etc. Okay, so these HDF files have a lot of complexity, and up here you get this almost directory-like structure. It has slash, and inside slash it has MDF. So EMAN follows a standard which was proposed for the whole structural biology community back in like 2005, 2006 or something like that. There was a white paper basically, that was published proposing how CryoEM data could be structured inside HDF files. And EMAN follows that standard for HDF5 files. However, if you use other HDF5 data saving libraries and stuff, you probably won't be producing data. You'll be producing valid HDF5 files, but they won't have the same internal structure as the EMAN produced ones, and then they won't be directly EMAN compatible. So that's sort of the disadvantage. You can have two HDF5 files, and not any program that uses HDF will necessarily be able to read them. If you look at a generic program like MATLAB, it will be able to sort of pull out data objects from HDF files irrespective of how they're structured. Basically, you'll look through the entire tree and find all the data objects and let you pull them out. But EMAN will only recognize HDF files that are structured like EMAN files. Now, why is this important? If you convert an EM data object into, say, a NumPy object, right? If we import NumPy as NP, and then we, well, just do that first, and then we'll say AA is equal to A dot NumPy. Now I've got my NumPy representation of my EM data object. There are Python libraries which, like H5PY, H5PY is an example of one. I might even have it here. let's see. Yeah, so it's even available here, which purports to write data like EM data, or sorry, like NumPy arrays into HDF5 files. And it will, but it won't write them into HDF5 files in the same way EMAN does. So this library massively simplifies HDF5 files. So you can only write certain types of raw image information into the files. And if you write files this way, you won't be able to read them back in EMAN or in Chimera, or, well, actually Chimera you might be able to, because Chimera actually uses this library for some purposes. But it won't be sort of, you won't have header information. You won't be able to do a lot of things with it. So you shouldn't use libraries like this. Now, the reason I mentioned this, aside from the fact that someone might think to do that, is that if you look at TensorFlow, once you've built up, say you use Keras and TensorFlow to build up a big neural network. So you've built this big neural network and you've trained the neural network, and now you need to save the trained neural network to disk. How do you go about saving that to disk? So there are two structures that TensorFlow provides for sort of easily saving these trained neural networks to disk. One of them is this really messy format, which basically makes a folder, and it puts a whole bunch of different files in the folder representing the different elements in the tree. So it'll write, a NumPy array for the, or, a TensorFlow tensor for the first layer, and then it'll write another one for the second layer, another for the third layer, all the separate files in the file system. So you don't have a file you can read again. You have a whole folder of files that you then have to read if you want to reload the network. Then it also provides an easy mechanism of dumping the whole TensorFlow trained network to an HDF5 file. That HDF5 file, like EMAN, will pretty much only be readable again by TensorFlow or by a generic package, which you can sort of tell it to read any part of the structure. So you could write that whole TensorFlow object to a single HDF5 file, and you can read it back again. And EMAN does this. So in cases where we do neural network training, we will actually store those objects as HDF5 files with a .h5 extension instead of an HDF extension. And you will not be able to open those H5 files as if they were image objects in EMAN, because they aren't. They're a whole set of TensorFlow tensors. We might be able to come up with some way of interpreting them as image objects of different sizes and stuff, but at the moment you can't read them. So that use of HDF5 files is another valid use, but it's also not an EMAN2 compatible use. So EMAN2 and IMOD and Chimera are the three CryoEM packages which all have some level of HDF5 support for the style of HDF5 files that EMAN2 uses. So you should be able to somewhat move your HDF5 files between EMAN2 and IMOD, although David Mastronardi just sort of started adding that kind of, over the last few years, and it may not be perfectly robust yet. Chimera definitely has support. Chimera added support like 12 years ago or something like that for the EMAN style HDF5 files following the same white paper and stuff. So you definitely can take EMAN2 HDF files and read them directly in Chimera, which is very convenient. Anyway, I wanted to clarify that because someone asked a question about it, and I thought it was important to understand what was going on here at least a little bit.
So is the you get a neural net out after your training,
yeah,
in like the segmentation procedure, yeah, for EMAN2. So is that it? You're saying that's an H5? I feel like I've seen like that.
It depends a little on the program. So with the Gaussian mixture model stuff, those networks are all being saved right now as HDF5 files. Some of Muyuan's earlier segmentation programs, I think you're right. I think he may be saving some of those, turning some of those into images and saving them as images, and then turning them back into TensorFlow objects or something like that. I don't remember off the top of my head. Certainly a lot of the output files that come from running the neural network, I mean, all of those are going to be image files, but the network itself in the early days, Muon did not save the network itself. He only saved associated files and then sort of rebuilt the network as necessary. But now it's become easier to save the networks. That HDF5 saving capability was broken apparently for a long time in TensorFlow. So it's only recently become possible to rely on it.
Okay.
So you're absolutely correct. You might find some places where EMAN isn't using that HDF5 mechanism in TensorFlow.
Okay.
Is there a library like MRC file for HDF5 files in the CryoEM sort of layout that you're describing?
Well, so the HDF5 file format has its own standard library. I mean, the HDF5 organization makes the standard HDF5 library. The issue is that it's generic, and you know, so the details about how the data is structured inside the file aren't embedded in here or anything like that. So if you want to be able to say read image number 1 from an HDF5 file, it won't provide that level of abstraction. You have to actually understand the file format yourself to deal with that. And no, nobody that I'm aware of has written an abstraction layer between the HDF5 library. You know, the problem is if you're going to write a generic library for reading, say, an MRC file, how do you return the results? You know, you then say, oh, well, okay, you can read it from the file and I'll present it to you as a floating point array and a dictionary of metadata objects, maybe. But, you know, there are so many different ways you could present the information that it's almost not worth the effort. So yeah, I agree. And that's one of the reasons why HDF5 has not become a widely used standard in the community, is because there is a bit of a pain factor involved in implementing an actual usable reader for the CryoEM community from the existing HDF5 library. On the other hand, as I've pointed out many places, including the HDF5 data compression paper we just published recently, the most complicated file I/O object in terms of code in EMAN2 is the MRC file I/O object, because so many different people have modified the standard on their own over the years and used it for incorrect purposes. Right, so people have added, oh, I'm going to use the extra the extended header with my header, and then someone else says, oh, I'm going to use the extended header with my header, and there's no way of identifying which of the headers are there. So when you read the file, you have to somehow look at it and figure out which type of header it is. And there have been all sorts of things that people have done which have just been horrible. So MRC files, while they are a standard, and while there's a paper which describes the standard, real HDF5 files, real MRC files, in the community are all over the place. And I don't know how good that standard HDF5, that standard MRC reading library actually is in terms of being able to handle every possible variant.
Yeah, that's it's something I've struggled with, is especially getting older software to read newer MRC files.
Yeah. You can also run into issues where for a number of years, for example, David Mastronardi had misread, well, you could blame it on him or you could blame it on the people who wrote the standard, but there was a disagreement about whether 8-bit data should be stored as signed or unsigned values in the file. So if you look at MRC files produced by IMOD for about a 15-year period of time or something like that, they use the opposite of what the MRC standard actually was supposed to say. And he tried to kind of mitigate that problem later on and stuff like that. So any proper MRC reader also has to be able to try and detect those files that have signed data where it should be unsigned and fix it. Anyway, it's just a nightmare.
So I guess sort of while we're on this topic, I did read the most recent paper you mentioned. I wanted to reread it before I asked these types of questions, but
It's okay to ask.
so how are you saving data off of a microscope right now? Like dose fractionated movies.
Well, when you save movies, that the data compression stuff that we talk about in that paper is not appropriate for use with raw movies. Okay, raw movies, either you use the file format provided by the detector vendor. So, for example, if you're using a Falcon 4, they've got the EER format, which already does very nice compression of the sort of raw count data. Or compressed TIFF is a very reasonable way of storing it. There are limits to how compressible that is because it's basically 2 bits of data, and there's nothing you could truncate. Basically, it's basically at that level, at the level of individual frames, it's basically pure noise with a tiny amount of embedded signal that you can get when you average the frames together. So you really can't throw anything away with that data reasonably. So the only, the data compression that we're talking about in the paper really starts at the level of once you've done the movie average and done the gain normalization, that's the point at which it makes sense to, when you save those, you want to save them using the bit truncation scheme.
So you're taking these TIFF stacks that are already compressed as they're written in theory, and then frame aligning them, and then saving those aligned frames as compressed HDF with the bit truncation.
Yeah, so unless you're going to try and do very, very, so if you're going to do, polishing, particle polishing in Reliant or something like that, then it wants the raw movie stack per particle or something like that. But at some point, you still have to get to having that averaged movie, right? I mean, that micrograph. And the way that's being stored right now, it's like 10 times bigger than it ought to be. So people always have those floating around in their file system. Very often, they're almost as big as the original raw TIFF movies. Once you extract the per particle movie stacks, those per particle movie stacks are a lot smaller than the overall frame movie stacks, right? So you can start saving a little bit of space in your local file system that way.
So is there a motion correction software that will write out HDF files?
Natively, you mean?
Yeah.
I doubt it. I mean, I'm not aware. Motion Core certainly doesn't have HDF support in it. So
right now,
I'm not aware of anything that will immediately produce HDF files. You'd have to run E2proc2D and convert it to an HDF file, and then you can delete the MRC file.
Okay.
I agree. It would probably make sense to be able to do that directly. We had our own motion correction software in EMAN for a while, but it just became kind of pointless to try and compete with like Motion Core, which was focusing just on that motion correction step, and they were doing a pretty good job at it. So it didn't seem worth the effort to compete with that. Although I'll admit that it seems like there is further room for optimization in the motion correction arena again nowadays. I mean, now we're getting very different sorts of movies than the community used to get. Right now the frame rates that you can get out of the cameras can effectively go up to 100 frames per second or 150 frames per second or something like that. The current motion correction algorithms will handle that by just averaging it down to 20 frames a second before it tries to do anything, right? So there's probably room for some additional improvement still in that area, but it's an area of research in itself.
Yeah, it's kind of confusing because I can take the TIFF stack and run it through Motion Core, and then I get my dose weighted and my non-dose weighted, and then you sort of got to figure out the track for each of those outcomes, get them into HDF and bit truncate them, but then you're just swapping them around constantly. And it'd be real nice to have one HDF file with all of that information
You mean with both types of images in the same file?
Yeah.
I mean, sure, you certainly could store both the motion corrected and non-motion corrected, and maybe dose weighted and non-dose weighted. I mean, there's a bunch of different options there. You could put all of those in a single HDF file, but then you'd sort of have to keep track of. I'm not sure there's a lot of advantage to putting the different types of image in the same file. I think if I think of my own workflows, I would probably make each of the types of files and for all the micrographs and put them in a named folder, describing what it is. And then I'd sort of swap the whole folders out if I wanted to change my processing pipeline around. You know what I'm saying?
Yeah, I think I get the idea, because EMAN2 will just assume it's the same thing as long as it has the same name.
Well, and the
so
same
if you
thing is
have-
true of Reliant or anything else that you want to use, as long as it's if you've got your star file, which is referencing images in another file, you can just rename the folders basically, and you can produce the same sort of result. That's usually the most reliable way of handling that kind of thing in my experience. I mean, if you're right, you could put it all in the same file, but then you would have to have software which said, oh, you're asking for this image from this HDF, this type of image from this HDF file. And then you'd sort of have to integrate that into your entire pipeline, right? Whereas if you just implement it by keeping the files in organized folders, then you don't have to worry about any changes to the software at all. Anyway, there's lots of different ways to solve any problem.
Yeah, I appreciate your thoughts on that. We're still trying to figure out sort of what the workflow is to teach people as they use stuff. So
yeah,
got to figure it out ourselves.
Unfortunately,
first.
the answer is there isn't only one. Okay, well, we've been going for a bit over an hour now. Unless other people have questions, we can end for the day.